This is a continuation of the little series that we're doing on group actions, specifically groups acting on sets. And today we're going to talk about Burnside's theorem. And we're going to use some of those definitions from those previous videos, so make sure to check those out if you need to. So in particular, we're going to use the notion of a G set, or G acting on a set X, as well as the stabilizer subgroup of an element. And all of this is motivated by the following type of question. And that is, how many ways can we color the vertices of a square with blue or magenta up to rigid motions? And so what do I mean by up to equivalence by rigid motions? Well, it means something like this. So let's consider these two squares with the following coloring. So let's say we've got blue right there, and then magenta everywhere else. So this first square, we've got blue in the upper left, and maybe in this second square, we have blue in the lower right. But let's observe that we can apply, well, either a reflection about the diagonal or a 180-degree rotation and turn this first square into the second square where the coloring is occurring exactly at the same place. So, well, what we want to do is consider these two as having the same coloring. And, well, notice that that coloring is equivalent up to acting by rigid motions, but we have a group of rigid motions in this case, and that is a dihedral group. So perhaps there's something we could do to answer this question involving the structure of that dihedral group, and there is. And so let's start down the path to seeing this structure, which is going to eventually become Burnside's theorem, and we're going to start with the following lemma. So let's say we've got G acting on a set X, and we have two elements, X and Y, in our set X that are related via the group. And so, well, what does this mean to be related via the group, or be G equivalent? Well, that means that there exists a little g in capital G such that Y is equal to G dot X. Whereby G dot X, I mean the action of the group on the element of this set. Okay, so if we have that as our hypothesis, then the stabilizer subgroup of X, G sub X, is isomorphic to the stabilizer subgroup of Y, G sub Y. In particular, they have the same cardinality. Okay, so let's get to it. So let's start with, well, what we have over there. So since X is G equivalent to Y, there exists a little g in big G such that Y is equal to little g dot X. Okay, and now let's note this. So if A is in the stabilizer subgroup of X, then what do we know? Well, notice that this A is an element of the group. So since it's an element of the group, we can talk about how it acts on the set. But we don't know how it acts on the set as a whole, but we do know that if it acts on this single element X, it fixes that element X. That's what it takes to be inside of the stabilizer subgroup. So in other words, we know that A dot X is equal to X. X is fixed under everything in the stabilizer subgroup. And let's note also the following. Let's look at GA G inverse acting on perhaps Y. But let's notice that by our rules for a group action, that's going to be the same thing as GA acting on G inverse acting on Y. But since Y is equal to G acting on X, that means that X is equal to G inverse acting on Y. We did calculations like that in the previous video. So that's going to give us G dot A dot X, where I kind of combined the fact that this was X with our rule for the group action where I can split those up. Okay, but then we know that A dot X is equal to X because A was in the stabilizer subgroup of X. So this turns into G dot X, but we know G dot X is Y. So let's see what's just occurred. We found that if A was in the stabilizer subgroup and G was this special element that transported X to Y, then if we take GA G inverse, so that conjugate element, and act on Y, we get exactly Y. But observe, that means that Y is, or sorry, not that Y, that GA G inverse is in the stabilizer subgroup of Y, because this GAG inverse, well, fixes Y. Okay, good. And that motivates the following map. So we'll call that phi, which goes from GX to GY, defined by phi of A is equal to GAG inverse. So of course we know by this calculation up here that in fact it does take elements of GX and sends it to elements of GY. Now we just have to show that it's a homomorphism, and then we also have to show that it's injective and surjective. And that will show that we do have an isomorphism between these two groups. So how do we show that it is a homomorphism? Well, it's actually not so bad. Let's say we've got phi of AB, where A and B are both in G sub X. So we could write that as, let's see, GAB G inverse, but now we can stick a GG inverse between A and B. So we have GA G inverse and then GB G inverse. Because of course G inverse G is the identity, so that would kind of disappear if it were in between A and B. But now this is immediately phi of A, phi of B. So it is a homomorphism. Okay, good. Now let's show that it's injective, but that actually isn't too bad. Recall that homomorphism is injective if and only if the kernel is trivial. So let's suppose we have something in the kernel. So let's suppose that A is in the kernel of phi, but that's equivalent to saying that phi of A is equal to the identity. That's what it means to be in the kernel. But then by the way that we have defined our homomorphism, that's the same as saying GA G inverse is equal to the identity. But just by left and right multiplying by G and G inverse appropriately, we're going to get that A is equal to the identity. But that means that what we have shown is that the kernel of phi is simply the identity, which means that it is injective. That's equivalent to it being injective. Okay, so now we need to show that it's also surjective. So how can we do that? Well, let's take, perhaps we'll call it B. I know we used B up here, but we'll use it again. And let's say that it's in G sub Y. But now let's observe, and maybe I'll let you check this, that means that G inverse BG is inside of G sub X for essentially the same reason as we did up here. But now let's note, if we set A equal to G inverse BG, then phi of A is pretty clearly equal to B, just by a quick calculation. Again, I'll let you fill in the details if you need to. Okay, so we've got a homomorphism that is bijective, meaning that we have an isomorphism between these two groups. But I guess one of the upshots of that is that those two groups have the same cardinality. Okay, great. So now let's move on. Okay, so now for our big result, which is Burnside's theorem. So let's see what it says. So let's say we've got a finite group G acting on a set X. Then it says that the number of orbits of X is equal to 1 over the size of G times the sum as G goes over through all of the elements in the group big G of X sub G, or the size of X sub G, I should say. And what's the size of X sub G, or what is X sub G, I guess is most important? Well, this is going to be all the elements of X that are fixed by G. So we'll write that down in just a second. Now, put in terms of our opening question, that means that if we consider X to be the set of all unreflected and unrotated colorings, then these two objects are in the same orbit. And the same orbit being there is a path to go from one to the other by hitting with a particular group element. Okay, so let's maybe get into the proof. Okay, so let's start with the following observation. And that is if we take the sum as G goes over all group elements G of X sub G, the size of X sub G, which is almost all of the right-hand side here. Well, that's going to be equal to the sum over all group elements of the size of the elements of X in X such that little g dot X is equal to, let's see, little x. And all I did there is I took my X sub G and I replaced it with the definition of X sub G. Okay, nice. But now I'm going to change this to a double sum, and the double sum is going to occur just by writing an internal sum here for every element. So that's going to be like this. We'll have the sum over all G in G of the sum over all X in capital X, satisfying the rule that G dot X is equal to X, and we're simply adding the number 1 up a bunch of times. So notice that this inside sum, which maybe I'll put in these green brackets, is exactly calculating this number right here in just kind of a strange way. Okay, nice. But now what I'll do is I'll change the order of summation. And so that's going to turn into this. So we'll have the sum over all X in X, and then the sum over all G in G, satisfying the rule that G dot X is equal to little x. So now the condition has to go on the inside, but it's essentially the same condition, except it's restricting group elements instead of restricting set elements. And then, well, we're still adding up the number 1 over and over and over again. But now let's observe that we can take that second sum, and the inner part of the second sum I'll put in these orange brackets, and we can rewrite that as follows. So we've got our outside sum, the sum over all little x and big X, and this is going to be the size of the set of all G in G such that G dot X is equal to X. Okay, nice. But now observe that, well, just to keep it consistent, notice that this is what was in orange, just put into a set. Now, that thing that I'm underlining in orange is exactly the stabilizer subgroup of X by definition. So we can rewrite this as the sum over all X in X of the size of the stabilizer subgroup of X. And now we're going to recall something we get out of the lemma. So maybe I'll sneak that in here. So I'll just put by lemma, we have the following. If we take the sum over all y, not in x, but in the orbit of x, I'll let you look up the definition of the orbit from a previous video if you need to, of the size of g sub y, so the size of that stabilizer subgroup, what are we going to get? Well, we're going to get the size of the orbit of x times the size of g sub x. Well, and why is that? Well, notice that the size of g sub y is going to be equal to the size of g sub x. By our previous lemma, all of those stabilizer subgroups have the same size. So I'm simply adding the size of the stabilizer subgroup of x to itself the size of the orbit of x. Okay, cool. But then we can rewrite this as the size of the stabilizer subgroup g sub x times the index of g in g sub x. And that's from a result in a previous video where we proved the size of the orbit was equal to that index. But then, just by how the index works with the size of a subgroup, I guess really by Lagrange's theorem, we know that this product right here is the size of the entire group. Okay, so we did two like semi-unrelated looking calculations. Now let's maybe summarize them and then see how we can finish this off. Okay, so this is what we ended up getting on the last board, these two equations. And now we're ready to put them together. So let's maybe introduce some notation here. Let's say that n is the number of orbits of our set X. Okay, great. And now let's do this calculation. Let's say that n dot, the size of G, will be equal to what? Well, it's going to be equal to n dot, and then we can write the size of G as the sum over all y in the orbit of X of the size of G sub y by that first result. Okay, nice. But now what we can do is simply add this to itself, the number of times that we have the orbits of X. So let's do that. So here we're going to sum over all different orbits of capital X. And so that would be summing over these y's or something. And then inside of that, we're going to sum y in the orbit of little x and then the size of G sub y. So something like that. But now notice that summing over all distinct orbits of X and then summing over everything within each orbit is the same as summing over all of the elements of X. So this turns into the sum over all X in X of the size of G sub X, where I changed the size of G sub Y to the size of G sub X using our previous lemma. But then by this equation right here, we know that that's the sum over all G in G of the size of X sub G, or the stabilizer, or everything that's stabilized by G, the G invariant subset. Okay, great. So we've got this thing proven. Well, I guess I didn't say that explicitly, but notice that if we take this and divide both sides by the size of the group, we have built our equation over here. Okay, so let's see how we can apply this. So for our first example, let's look at our motivating question. That is, how many ways can we color the vertices of a square with either blue or magenta up to equivalence via rigid motions? And let's just point out that that's up to an action by the dihedral group D4. Okay, so let's maybe lay this out. So X is going to be all possible colorings. And so we talked about this before. It's all like possible colorings without considering them being equal if you have rotations and reflections. So we could write down a couple of these. I don't think we'd like to draw all of them, but let's draw a couple. So let's see, we could have one right here, which is perhaps all colored blue. That's definitely a type of coloring. We could have one that is blue with a single magenta in the upper right. So that's a definite other coloring. We could have one where it's all blue but a magenta in the lower right. That's definitely a coloring as well. And since we're not considering equivalence inside of this set, we would consider those second two to be non-equivalent. And then, well, I think you could draw the rest, but I won't do that. And I'd like to observe that we know the size of X as well. The size of X here will be 2 to the 4 power, or 16. And we know it's 2 to the 4 power because, well, notice that we've got 4 vertices to color, and we've got 2 choices. So 2 choices for this times 2 choices for this times 2 choices for this times 2 choices for this. That's obviously equal to 2 to the 4. And now, well, keeping this in mind over here, we need to think about what is fixed under each of the group elements. And let's just lay out D4 acting as follows. So of course you can define the reflection to be a number of different kind of elementary reflections, but we'll define it as follows. So let's say S is the reflection about this line right here. But then that means that S times R squared is going to be the reflection about that horizontal line. And then let's see, S times r will be the reflection by that diagonal that goes from the bottom left to the upper right. And then SR cubed will be the reflection about the remaining thing. So those are all our reflections. And then of course, by R, I mean a 90-degree rotation. Okay, nice. So now let's maybe get going. So let's see, we need to look at everything is fixed under the identity. Well, notice that the identity fixes everything. So that means that X sub E, things fixed under the identity, that's just the whole set. And now let's look at this. What about X sub R? And so that's going to be everything fixed under a 90-degree rotation, which that 90-degree rotation could go counterclockwise or clockwise, but going counterclockwise is R, going clockwise is R cubed, because R cubed is a 270-degree rotation counterclockwise, which is the same as a 90-degree rotation clockwise. And now what is fixed under these two? Well, you know, you can look at it a little bit, but you'll see after looking at it for not too long that there are exactly two colorings that are fixed under a 90-degree rotation. And those two colorings are the two, maybe what I'll call boring colorings, which are colorings with just all blue or all magenta. Okay, great. And now let's look at XR squared. So that's everything fixed under a 180-degree rotation. So let's see, we can draw some pictures of that too. Here we're gonna have 4 different types of squares that are fixed under this rotation. So let's see, we've got the square that's all magenta. We've got the square that's all blue. Those are again kind of the boring colorings. And then we've got the squares where the diagonals share a color. So let's see, we've got ones where the blue are upper left and lower right, and the magenta are the other two, and then vice versa. And if you look at these, notice that all of these squares are fixed under our 180-degree rotation because they bring the same color into the same color. But nothing else is fixed under that 180-degree rotation. Okay, so that takes care of all of our rotations. So this is like the 0-degree rotation, 90-degree and 270-degree rotation, and this is our 180-degree rotation. And now let's look at our reflections. And now the colorings that are fixed under S and the colorings that are fixed under SR squared are fairly similar. So let's draw those on the board real quick, and then we'll make a little argument why these are all of them. Okay, so let's see, XS is gonna be all of the colorings that are fixed under a reflection by this vertical line. So of course you're gonna get the two colorings that are monochrome, all blue or all magenta. And then you'll get the colorings where the top edges are the same, or the top vertices are the same, and the bottom vertices are the same. So you've got a choice for blue on the top, magenta on the bottom, or vice versa. But now if we look at SR squared, that's a reflection about this horizontal. So you'll get the two monochrome again, and you'll get the colorings where the left is blue, the right is magenta, or vice versa. So notice you get 4 colorings there as well. Okay, so now let's look at one more, and then we'll leave the last one kind of as a bit of a homework exercise. Let's look at XSR. So that's going to be a reflection about, let's see, this diagonal here from lower left to upper right. And we'll make a bit of a counting argument for this instead of drawing them all out, just, you know, for practice with a counting argument, and also because there are more in this case. Okay, so let's observe that if we are reflecting about this diagonal right here that goes lower left to upper right, we'll notice that that does not move this vertex, and it also doesn't move this upper right vertex. But that means that this lower left vertex can be anything at all, and it doesn't matter. It doesn't have to match with anything else because, again, it's not moving. Same thing for the upper right vertex. That being said, the remaining two vertices will map into each other, so these two have to be the same. So I'll just put free and same for, the colorings there. Well, what does that mean? Well, that means we have two choices for this lower left, two choices for this upper right, but then once we've chosen this, which has two choices, we have fixed this one. So our number here is 2 times 2 times 2, because again, this one is fixed. In other words, the size of SR is equal to 2 cubed or 8. And just, for the sake of argument, that's going to also be equal to the size of SR cubed for essentially the same argument or the same logic. It's just you're working off the other diagonal. Okay, so now let's check it out. We have counted everything we need to count. There are 16 elements here, and then there are 2 elements in this coloring, or in these 2 colorings, 4 here, and 4 here. So now we can apply our Burnside's theorem, and we'll get the number of orbits. But notice that the number of orbits in our case is the number of what I'll call inequivalent colorings. Whereby an inequivalent coloring, I mean that none of these 2 colorings can be changed from one to the other using a group element. And then this is going to be 1 over the size of the group. We know the dihedral group has 8 elements. And then, let's see, it'll be 16 plus 2 plus 2 plus 4 plus 4 plus 4 plus 8 plus 8. That's just adding up all of those right there. But then a quick calculation will show us that that is equal to 6. So that means that there are 6 inequivalent colorings. Okay, let's do another example. So for our next example, let's say we've got a cube and we want to label the faces of the cube with the numbers 1 through 6. But then we want those labelings to be inequivalent modulo, maybe tossing the cube like you would toss a die. So modulo any sort of rotation. So that means in this case, our group is the rotation symmetry group of a cube. And we'll talk through all the types of elements of that. And then our set X is the set of all unrotated labelings. But notice by a simple counting argument, there are 6 factorial unrotated labelings because you've got 6 choices for the first side, 5 choices for the second side, so on and so forth. And I guess I should say here, we're not repeating the numbers 1 through 6, just to be super clear. Okay, so now let's notice that if G is the identity, all of the unrotated labelings are fixed. I think that's pretty clear. Everything is fixed under the identity. So in this case, our X sub G, our size of X sub G, if G is the identity, is 6 factorial. But now let's look at all of these others. So let's look at this one, and all of these are going to kind of be silly, but we're going to do a follow-up example where we will use all of these group elements. Okay, so here's one thing you can do. You can take an axis of rotation between 2 opposite faces. So I've got the picture right here. And you can do either a 90-degree rotation or a 180-degree rotation. Now, I'd like to observe for a 90-degree rotation, there are exactly 6 group elements. Now, how do I get those 6 group elements that give you 90-degree rotations? Well, I've got a choice of opposite faces. There are 3 opposite faces I could choose for my axis of rotation. And then I either have a 90-degree rotation counterclockwise or a 90-degree rotation clockwise. So putting that all together, I have 6 non-identity group elements. But then if G is one of those group elements, notice that the size of X sub G is 0. And that's because, well, we're labeling all of the faces differently. And since we're labeling all of the faces differently, well, the only thing that could fix them would be the identity. So we'll see that all of these X sub G's are 0 in size. But like I said, we're going to use this setup for our next example. Okay, so now let's say we've got the same axis of rotation, but now 180-degree rotation. So let's observe here, there are 3 group elements that would satisfy this condition. And that's because, well, we've got 3 choices of the axis of rotation. But then if you do a 180-degree rotation, there's only 1 non-identity element. But like I said, all of the things fixed by non-identity elements here are going to be empty because we're labeling all of these cubes with different sides, or all of the sides with different numbers. So the size of x sub g here is 0. Now let's look at this 120-degree rotation between opposite diagonal vertices, or vertices that are opposite diagonals. So like I said, that's a 180-degree rotation, but that means that there are how many group elements like this? Well, there are 4 axis choices. So there's one like going from this bottom forward left to the top backward right. And then, well, there are going to be 4 more going through these 4 base vertices. So there are 4 axis choices. And then there are going to be 2 non-identity elements for each axis choice. And that's because you could have a 120-degree rotation counterclockwise or clockwise. So altogether, we're going to have 8 such group elements. But again, none of these will fix our labeling, so the size is 0. Okay, then we've got one more type of rotation, and that is through these opposite edges, these kind of diagonally opposite edges, and that gives us a 180-degree rotation. And in this case, we've got how many choices of opposite diagonal edges? We have 6 choices of opposite diagonal edges. So like from here to here, let's see, from down here in the left to up here in the right, and then we've got forward, backward, and side, side as well. So again, like I said, we've got 6 choices for these opposite diagonal edges, which means in total we've got 6 group elements. But again, as boring as all of the others, if G is one of these group elements, everything fixed by G is just empty because we're labeling all of the sides of this cube differently. So now let's see, putting this all together, we have the number of orbits, but in this case, the number of orbits is the number of ways that this cube can be labeled. Keeping in mind that we're labeling modulo rotations, will be equal to 1 over the size of the group. But if you count this up, you'll pretty quickly see that the size of the group is 24 times the size of all of these xg's summed. But notice that's simply going to be 6 factorial plus a bunch of zeros. Here you nominally have 6 times 0 because you've got 6 group elements, but the size of all of those sets is 0, so you have 6 times 0. But if you wanted to put the structure in it, that's how you would count that up. Here you would have 3 times 0. For all of the rest of them, you would have something times 0 as well. So in the end, you get 6 factorial over 24. But then if you were to do that calculation, you pretty quickly see that that calculation is 30. So there are 30 different ways to label this cube. Okay, so now let's do a follow-up example to this that's a little bit more interesting. Okay, for our follow-up question, we want to see how many ways can we label the faces of a cube with 2 1s, 2 2s, and 2 3s, where these are rotationally inequivalent, just like before. And so again, our group is the rotations of a cube, and then the number of unrotated labelings is a little different here. And how could we count this up? Well, I'm gonna jot it here kind of in the margin, but the way you wanna think about this is you initially wanna think about all of these as being different. So perhaps you would think about initially as this being magenta 1, 2, 3, and then perhaps yellow 1, 2, 3. And so that would give you an initial number of labelings as 6 factorial. But then after that, you would forget the coloring and you would notice that, well, now we could switch the 2 1s and we would have an equivalent labeling. So we would divide that by 2. And then we could switch the 2's and we would have an equivalent labeling. So that would be another division by 2. And then finally, we could switch the 3's and we would have an equivalent labeling. And that would give us another division by 3. So in the end, there are 90 such unrotated labelings. But now let's go through each of the group elements and count what's fixed under these group elements. Okay. So let's start with G, which is the identity element. Well, obviously everything, all 90 unrotated labelings are fixed under this identity element. That's no surprise. Now let's look at this 90-degree rotation. Well, I claim that in the 90-degree rotation, still nothing is fixed. And that's actually pretty easy to argue if you think about it like this. A 90-degree rotation has to be repeated 4 times in order to get back to the identity. But that means that 4 sides would have to have the same number if our labeling was fixed under this group element. So for instance, if I were rotating about the axis shown here, and this front face were a 1, well then my 90-degree rotation would tell me that this top face would also have to be a 1. But then, applying the 90-degree rotation again, that means this back face would have to be a 1, and then finally this bottom face would have to be a 1, but I've used too many 1s. So, like I said, the number of group elements fixed under this will be 0. Okay, so now what about 180-degree rotation about this axis? Well, in this case, you get stuff that's fixed. So we've got the size of the fixed point subset here will be equal to 3 factorial. And well, let's argue why that's the case. Well, notice that if we're rotating about this axis, the 2 faces on the side have to be the same. But how many choices are there for those 2 faces on the side? Well, there are 3 choices. So I've got 3 choices for the faces on the side. But then again, if I'm making this 180-degree rotation about this axis, the front and the back face have to be the same. But now I've got only 2 choices for that because I've used my choices for the side. And then after I've used the first choice and the second choice for my 2 sides and my front and back, I'm left with only 1 number that I can put on the top and the bottom. So again, I've got 3 factorial possibilities here. Okay, great. But now let's move on to the next type of group element, which is a 120-degree rotation about this diagonal. But again, I'll argue pretty quickly that the number of colorings fixed under this kind of operation is 0. And that's because, well, this is like a 3 cycle. You have to apply it 3 times to get back to the identity. But that means that anything that you started with on one face would have to be repeated 3 times in order to be fixed under this type of action. But of course, we only have 2 copies of 1, 2 copies of 2, and 2 copies of 3, so that's impossible. And now let's move on to this one down here where we're doing our 180-degree rotation about this axis through diagonally opposite edges. And in this case, the number of group elements that are fixed is 3 factorial again, for the same kind of argument that we had before. So if we're rotating about this axis right here, let's observe that the face in the front here has to match the face on the side. So we're choosing a number for each of those 2 faces all at once. We've got 3 choices. And then the face on the top is going to rotate into this face on the left. So there's now 2 leftover choices for those faces. Remember, we're choosing those both at the same time because they have to be the same. And then likewise, there's going to be 1 choice for what's left over. In the end, there are 3 factorial. Okay, so now let's answer our final question, which is how many ways can we label these up to rotation? And the answer here is going to be 1 over the size of the group, which is still 24. And then we'll have 90 for everything fixed under the identity, plus 3 factorial times 3, and that's everything fixed under one of these 180-degree rotations here. 3 factorial by our counting argument, and then times 3 because we've got 3 group elements that do that kind of action. And then plus 3 factorial times 6. Again, that's for this 180-degree rotation about these axis through these edges. And that's by our counting argument times the 6 group elements. But now you can do that calculation. What you'll see is you get 6. So there are 6 different inequivalent labelings of a cube with 2 1s, 2 2s, and 2 3s. All right, now I'm going to leave you with some homework exercises. All right, here are 3 exercises. The first one is to exhibit Burnside's theorem with the following group. So it's a subgroup of S5 generated by 1, 3, and 2, 5, those 2 transpositions. And our set X is simply the set 1, 2, 3, 4, 5, and the action is kind of the obvious action of S5 on that set. Next, how many ways can the vertices of an equilateral triangle be colored with 3 colors modulo rigid motions? And so that would be all of the dihedral group. And then next, how many ways can the faces of a tetrahedron be colored with 2 colors up to rotation? So let's just recall a tetrahedron is this like 4-sided 3-dimensional shape that I've drawn down here. And that's a good place to stop.